Assalamu alaikum and greetings everyone, and welcome to video 1.1a based on physical quantities. In this video we'll be covering the definition of physical quantities with some common examples and the units we use for them. We'll be covering standard form and prefixes to represent very large or small values. We'll be covering vectors and scalars as two types of physical quantities and comparing some common examples. Finally, you'll be introduced to the resultant vector, more details of which will be covered later. So what is a physical quantity? As the name suggests, it is a physical property of something, and quantity means it can be measured. So it has a magnitude, that is the size of the quantity, and it has a unit that identifies which quantity is being measured and in which units. So for example, if you look at distance, a distance of 5 meters means the size of the distance is 5 units, and meter is the unit. And meter, as you will see later, is the unit for distance, and it also means it's being measured in meters and not kilometers, for example. Now let's look at some common examples and their units. The quantities given below are known as base quantities, and most of the other quantities that you will see in this course and they will be introduced later would be derived from these basic quantities. Okay, so let's look at length. Now length is measured in the SI unit meter with the symbol m. However, in a formula you would not write it as m. For example, speed equals distance upon time, right? So distance over here would be denoted by a d. Okay, so you can use L, H, D, S or X, whatever fits there, whatever you want to use. Other units would be kilometers, centimeters and millimeters. You should know that the SI unit is the international standard unit for the quantity. It's the quantity you would use to write your answers in. But you can also use kilometer, meter, millimeter or centimeter. Okay. Now looking at mass, the SI unit here is kilograms. This is interesting and a very common confusion because the SI unit has a prefix. Okay, it's not grams, it's kilograms. But you can measure mass in grams and milligrams as well, and whatever other prefix you will see later. For the other quantities, you can just look at the table. You have the SI unit symbol. Please be careful. For example, meter, kilogram and second are in lowercase, but current and temperature would be uppercase A and K. Okay, just look at the formula standards, the SI unit standards and the other units you can use. What if you had a number that is too large or too small to be written on a paper, or it has so many zeros that it's very difficult to keep track of them? For example, the distance between the earth and the sun in meters, or the size of an atom in meters. This will be very difficult, and what we have to fix this is this system called standard form. What we do here is that we would move the decimal point to right after the first non-zero digit. Okay, so it would end up looking like a number between 1.0 and 10.0, and then because you've moved the decimal point, you would multiply the answer by a certain power of 10 in order to show the reader how many units that decimal point has jumped. So for example, if you look at 0.7 zeros and then 786, you would have to move the decimal point 8 units to the right so that it comes after the first non-zero digit, that is 7. Right? Now to tell me that you've moved that decimal point 8 units to the right, you would multiply it by 10 to the power minus 8. Similarly, if you have 786 and then you have 7 zeros, you would move the decimal point 9 units to the left. So you would write it as 7.86 into 10 power 9. Now, in this number, 786 and then 7 zeros, you should know that you cannot see the decimal point, and therefore you would assume that it is right at the end of the given number. Okay? Now, in your answers, if your number is too big or too small, you would be expected to use standard form and then give the SI unit at the end. Once you've got your number down in standard form, you can choose to replace your exponent with one of these prefixes. The table given shows you the prefixes you can use in your paper. Okay, so if you had, for example, 7.86 into 10 power to the power 9, you could see 10 power 9 is the same as Giga, so you could write 7.86 into 10 power 9 meters as 7.86 gigameters. But on the other hand, if you look at 7.86 into 10 power minus 8, now minus 8 does not have a prefix related to it. But if you look at 10 to the power minus 9, which is nano, let's see, 10 to the power minus 9 multiplied by 10 should give you 10 to the power minus 8, right? So why not write 7.86 into 10 power minus 9 into 10, right? Which would basically mean 7.86 nanometers into 10, and then you can write it as 78.6 nanometers. Here I've got some examples for you to try out. Pause the video, and first of all you would convert each of the numbers to standard form, and then you would put up a correct prefix for it. If you can convert it directly to the right prefix, that's well and good. If you need to, you might have to move the decimal point a little bit to the right in order to get one of the prefixes to fit. Okay, try them out and put your answers in the comment section, and I'll get back to you ASAP. Right, now let's look at the two types of physical quantities. A physical quantity that has a direction added to it is a vector, otherwise it's a scalar. A vector can be positive or negative depending on the direction. If the direction changes, the sign would be flipped. Scalars are always positive because, they don't have a direction, so they don't need a sign. Vector examples are displacement, force, weight, velocity, acceleration. The others, we'll keep looking at them as we go along. Scalar examples would be distance, speed, time, mass, energy, and temperature. For example, if you look at temperature doesn't really have a direction. It's just a quantity that exists. Whereas, on the other hand, weight is a vector acting in a specific direction downwards, right? And therefore, it's a vector. We'll look at some examples to make this even clearer. So, let's look at distance and distance with a direction, that is displacement. They both measure length and have the same unit, but displacement is the vector. So looking at the example on the left, if you go from park A to your house B to park C, you look at the pink line that shows the actual distance that you're covering. You're covering 4 plus 3 is 7 meters in total. On the other hand, if you look at the displacement of the tree from the park A, the displacement is going to be a straight line from A to C, the shortest distance between the 2 points, and that would be just 5 meters. So the displacement has a specific direction, so it's 5 meters somewhat northeast of point A. But the distance covered is the actual length that you cover moving from A to C. On the other hand, if you look at the second picture I've given, you start at the starting point, you move 2 units to the left, and then you move 4 plus 2 is 6 units to the right to end at the ending point, right? What is the total distance covered? Well, I move 2 units to the right and 6 units to the left, so it's 2 plus 6 is 8 units. That is the total distance I've covered. However, the displacement of the blue dot from the black dot is just the shortest distance between them. Okay, so I start at the start position and I move 4 units to the right to get to the end position. So the displacement is 4 units. If you ask me what's the displacement of the green dot from the black dot, it's just 2 units to the left. Another example would be of speed versus velocity, where speed is rate of change of distance, velocity would be rate of change of displacement, or essentially speed with a direction attached to it. So if speed tells you how fast you're traveling, velocity would tell you how fast you're traveling in a specific direction. So 20 meters per second is speed, but 20 meters per second towards the east is velocity. Now, because vectors have a direction and a size as well, you can add 2 vectors together to find out the overall effect produced by them. So for example, you have a box, I'm pushing it towards the right and you're pushing it towards the left. Okay, the resultant vector is what's going to tell me what the eventual force is acting on the box, and it's also going to tell me what direction the box would end up moving in. Okay, depending on which force is stronger, the object would end up following that force. Okay, We'll be looking at this in more detail later on. But for now, just know that you can add up vectors and individual vectors add up to have a final effect altogether. That's it for this video. Thank you for watching. I hope it's all clear. If you have any questions, you can hit the comment section anytime. Thank you.